Hello, I'm Sungjae Hong from the Mobile Networking Lab. Today I'm going to introduce the paper called Maximizing the Spread of Influence Through a Social Network. The order of presentation is as follows. When we use social media like Instagram and Facebook, we find it easy that there are lots of advertisements. Some of those advertisements might be useful, but if they are too much and irrelevant to the viewer, people wouldn't like it. However, people tend to be convinced more when his or her close friend recommends any product, because we recognize our friend more reliable than social media. For the product seller point of view, it is efficient to choose small amount of individuals that can spread and advertise their product well. In other words, by initially targeting a few influential members of the network, for example, by giving them free samples of the product, they can trigger a cascade of influence by which friends will recommend the product to other friends and many individuals will ultimately try it. So the question is, how do we know those potential influential customers and how to maximize the spread with minimal individuals? First, let's see two basic diffusion models and find out how spread works in network. In considering operation model for the spread of an idea or innovation through a social network G, represented by a directed graph, we will speak of each individual node as being either active or inactive. We will focus for now on the progressive case in which nodes can switch from being inactive to being active. This model is called linear threshold model. A node V is influenced by each neighbor W according to a weight B VW shown in the picture. The total number of this weight per node is smaller or equal to 1. Each node V chooses a threshold theta V uniformly at random from the interval from 0 to 1. Given a random choice of threshold and an initial set of active nodes A0 with all other nodes inactive, the diffusion process unfolds deterministically in discrete steps. In step T, all nodes that were active in step T minus 1 remain active, and we activate any node V when the total weight of its active neighbor is at least theta V. We can also consider dynamic cascade models for diffusion processes. This is a conceptually simplest model which called the independent cascade model. We again start with an initial set of active nodes A0, and the process unfolds in discrete steps according to the following randomized rule. When node V first becomes active in step T, it is given a single chance to activate each currently inactive neighbor W1 or W2. It succeeds with a probability PVW1 or PVW2 shown in the picture. If W1 or W2 have multiple newly activated neighbors, their attempts are sequenced in an arbitrary order. If V succeeds, then its one neighbor node will become active in step T plus 1, and the process runs until no more activations are possible. We are now in a position to choosing a good initial set of nodes to target based on two models above. Both involve an initial set of active nodes A0 that starts the diffusion process. We define the influence of a set of node A, denoted sigma A, to be the expected number of active nodes at the end of the process, given that A is this initial active set A0. The influence maximization problem asked for a parameter k to find the k-node set of maximum influence. It means that the chosen set A of k initial active nodes has been targeted for activation by the algorithm. It is NP hard to determine the optimum for influence maximization. Our first main result is that the optimal solution for influence maximization can be efficiently approximated to within a factor of 1 minus 1e minus epsilon in both the linear threshold and independent cascade models. Here, e is the base of the natural logarithm and epsilon is any positive real number. This means that performance guarantee slightly better than 63%. The paper proved this result in using the theory of submodular function. To prove approximation guarantees, consider an arbitrary function f that maps subset of a finite ground set U to non-negative real number. We say that f is submodular if it satisfies a natural diminishing returns property, which is the marginal gain from adding an element to a set S is at least as high as the marginal gain from adding the same element to a superset of S. There is a theorem which is for a non-negative monotone submodular function f, let S be the set of size k obtained by selecting elements one at a time, each time choosing an element that provides the largest marginal increase in the function value. Let S star be a set that maximizes the value of f over all k element sets. Then it satisfies the inequality shown above. Our strategy will be to show that for the models we are considering, the resulting influence function sigma is submodular. In addition to obtaining worst-case guarantees on the performance of our approximation algorithm, they compare the performance of several algorithms. The dataset was a graph obtained from co-authorship in physics publications. For each paper with two or more authors, they inserted an edge for each pair of authors. Notice that this results in parallel edges when two researchers have co-authored multiple papers. They kept these parallel edges as they can be interpreted to indicate stronger social ties between the researchers involved. The resulting graph has 10,748 nodes and edges between about 53,000 pairs of nodes. They compare the algorithms in three different models of influence. In the linear threshold model, we treated the multiplicity of edges as weights, and it is shown above. In the independence cascade model, they assigned a uniform probability of p to each edge of the graph, choosing p to be 1% and 10% in separate trials. Lastly, in the weighted cascade model, each edge from node U to V is assigned probability 1 divided by degree dV to activate V. They used four different methods: greedy, high degree, central, and random. Greedy indicates greedy hill climbing algorithm, which performed the best. The high degree heuristic chooses nodes V in order of decreasing degrees dV and is known as degree centrality. Distance centrality is selecting nodes in order of increasing average distance to other nodes in the network. In particular, nodes in the largest connected component will have smallest average distance. Finally, we consider as a baseline the result of choosing nodes uniformly at random. The first graph on the left shows the performance of the algorithms in the linear threshold model. The degree algorithm outperforms the high degree node heuristic by about 18% and the central node heuristic by over 40%. The second one shows the results for the weighted cascade model, although the scale is smaller, but it looks similar to the linear threshold model. The graph on the left is result of the independent cascade model with probability 1%. It has very different scale. On average, each target node only activates 3 additional nodes. Hence, the network effect in the independent cascade model with very small probabilities are much weaker than in the other models. The graph on the right is results of the independent cascade model with probability 10%. Choosing K randomly starts to outperform both the high degree and the central nodes heuristic when more than 12 nodes are targeted. The first targeted node, if chosen somewhat intentionally, will activate a large fraction of the network, in our case almost 25%. However, any additional nodes will only reach a small additional fraction of the network. In particular, other central or high-degree nodes are very likely to be activated by the initially chosen one, and thus have hardly any marginal gain. This explains the shapes of the curve for the high degree and centrality heuristics, which led up to about 2415 activated nodes, but make virtually no progress afterward. The degree algorithm, on the other hand, takes the effects of the first chosen node into account and targets nodes with smaller marginal gain afterward. Hence, its activate set keeps growing, although at a much smaller slope than in other models. They proposed expressing the notion that a node V's decision to become active can be based on an arbitrarily monotone function, which contains the set of neighbors of V that are already active. By associating with V is a monotone threshold function fv that maps subsets of V's neighbor set to interval from 0 to 1. In the linear threshold model, each node V initially chooses theta V uniformly at random from 0 to 1. Now, however, V becomes active in step t if function fvs is greater or equal to theta V, where S is the set of neighbors of V that are active in step t-1. We generalize the cascade model to allow the probability that U succeeds in activating a neighbor V to depend on the set of V's neighbors that have already tried. Thus, we define an incremental function PV U as interval from 0 to 1, where S and U are disjoint subsets of V's neighbor set. In the general case, when U attempts to activate V, it succeeds with probability PVUS, where S is the set of neighbors that have already tried and failed to activate V. The independent cascade model is the special case where PVUS is constant PUV, independent of S. We will only be interested in cascade models defined by incremental functions that are order-dependent in the following sense. If neighbors try to activate V, then the probability that V is activated at the end of these attempts does not depend on the order in which the attempts are made. We have thus far been concerned with the progressive case in which nodes only go from inactivity to activity, but not vice versa. The non-progressive case in which nodes can switch in both directions can be reduced to the progressive case. Let's say S is the set of neighbors of V that are active in step t-1. Let A be a set of k interventions. The influence of these k interventions, sigma A, is the sum over all nodes V of the number of time steps that V is active. The influence maximization problem in the non-progressive threshold model is to find the k interventions with maximum influence. It shows that the non-progressive influence maximization problem reduces to the progressive case in a different graph. Given a graph G and a time limit tau, we build a layered graph G tau on tau multiplying V nodes. There is a copy node Vt for each node V in G, and each time step t is smaller or equal to tau. We connect each node in this graph with its neighbors in G indexed by the previous time step. The non-progressive influence maximization problem on G over a time horizon tau is equivalent to the progressive influence maximization problem on the layered graph G tau. Note V is active at time t. In the non-progressive process, if and only if Vt is activated in the progressive process. The probability that node V will become active is determined by the strategy and denoted by HVX. We assume that this function is non-decreasing and satisfies the following diminishing returns. We are trying to maximize the expected size of the final active set. As a function of the marketing strategy X, each node V becomes active independently with probability HVX, resulting in a random set of initial active nodes A. Given the initial set A, the expected size of the final active set is sigma A. The expected revenue of the marketing strategy X is shown above, which is function gx. In order to approximately maximize g, we assume that we can evaluate the function at any point x approximately and find the direction I with approximately maximal gradient. The proof that this algorithm gives a good approximation consists of two steps. First, we show that the function g we are trying to optimize is non-negative, non-decreasing, and satisfies the diminishing returns condition. Second, we show that the hill climbing algorithm gives a constant factor approximation for any function g with these properties. And proving those two guarantees the revenue, and we can find the approximation of optimal value. Here's the reference that I used to describe concepts in the slide. This is the end of my presentation. Thank you for listening.